My talk is about building your own programming language and using JavaScript. Traditionally, most language building tools are, say, in C or C++ or some other type of language that's more, in the operating system, one of those kind of languages. JavaScript is usually been used in the browser, but now we have environments like CommonJS, Node. You can do these kind of things just on your command line without using a browser. The basic idea I want to get across before we dive into it is, every program we write is basically an interpreter. We get data as input. We execute based on the rules of the program. But some programs take other programs as input, and so the other program is transformed into data, and the program, our compiler or our interpreter, executes rules based on how we want those that structure to be interpreted. So, program equals data. And basically, a compiler is, just a translator. So you take one language, you figure out what the meanings are of the symbols, the words in the language, and you output another language. So, Google Translate is a compiler of, say English to Spanish or something like that. So same basic idea. And this is just a basic ordering of how things go. First, you have your parser, which handles the syntax of the language. It figures out what the characters mean, what the words are, and like what sentences are valid in the language. And if you do a syntax error, that's like a malformed sentence in your language. Semantic analysis, we won't do much of that. That's stuff like if you want to do type checking, make sure things are, correct. But we'll basically print out what we get in another language. And that's at the bottom, code generation and your interpreter. And of course, all of this is going to be done in JavaScript, so it's easier for all of us to hack on and maybe come up with some new ideas, since JavaScript programmers are coming in lots of different varieties. So the first thing we need to handle the syntax is we're going to use a Parser Generator. You could, of course, do some ad hoc form of, reading each character in a string input or something, and roll your own way to interpret or parse the language. But we're going to use a Parser Generator, which sort of makes things easier. And these are a few available ones in JavaScript: Ometa.js, JSON, and peg.js, and JSCC. And those two are kind of newer. I like those ones a lot, but JSON is the one I wrote, so we're going to be using that one today. And Jeremy, who did a talk on CoffeeScript earlier today, he used JSON for that language to do the parsing phase of it. And he says it's a lot faster right now than the other ones, which, okay, I'll take that. So first, we need a grammar. A grammar describes, what valid tokens are and the structure of it. So I don't know if you guys have ever checked out a language specification before. If you've, this is a snippet from the ECMAScript specification, the 5th edition, so it just came out. And this is the JSON. Since JSON was added to the language, they have a grammar describing JSON right there. And our Parser Generator takes in a description basically just like that. And, live demo. So, I gotta kind of move the window from this view to the other one. Uh-oh. Where did it go? My window kind of ran away. Well, if I can't find this window soon, hold on, let me, actually, where's my mouse? I'll just open up a new window. And where is it? Yeah, this is when I bring out the command line, and this started out mostly like all live demos do. So, well, I can show you the command line version. I was going to show you the website, but that's all right. Let me just bring over the shell and ooh, that's not the right one. So the grammar file has a extension of JSON, which is the grammar format, and has anyone ever heard of Bison? Okay, yeah. So we have some language people in here. It's basically the syntax of the actual grammar format is almost basically the same as Bison syntax. So it makes it easy to port grammars that are already written for Bison, which are a lot because Bison and the Yak have been around I don't know however many years. So, and what I've defined here is basically a simple language. It only has variables that you can assign a value to, and then the plus expression, so you can add variables together and assign it to another variable. So, very simple syntax, and the first line is basically saying ignore white space. Yeah.
Increase the font.
Yeah, let me zoom in a little bit. Yeah, it's hard on this screen. All right. Yeah, so that's better. So the first line basically says ignore white space. So we don't care how much white space is between two tokens in the language. So you can have a variable equals and then like a long line of white space, a number or something like that. Actually, let me show you just an example of I'm not sure what. All right, so an example of the language. So our language is actually just going to look like this. X equals 5, or instead of using an equal sign, that's kind of boring, we'll use X is 5. Let's say Y is 6, and Z is X plus Y. All right, so that's going to be the syntax for the basics of our language, and we'll have a sort of a built-in method to show the value of that. All right, and all right, so keep that in mind. All right, so back to the grammar. All right, so that's how you can make sense of what these mean a little better now. Right there, you're saying is, and you're returning what is the token. So you're basically saying match these. This is a regular expression on this side. Match the exact characters is, and then return a token, which is the is token. And for show, it's the same thing. You're matching that. Those are like keywords. So you match that keyword. You return show, the show token. And you can see a number is just a regular expression returning the number token. And this is also, if you're familiar with Bison, you're probably familiar with flex, which this syntax tries to mimic the flex syntax, so it's easier to port existing grammars and that. And the rest of them you can kind of see, and there's a special one for the end of the file. All right, and so this is, and unlike Bison and Flex, we actually have the lexical scanner stuff inside of the Bison file, so it's easier to just combine it and not have two files. Basically, I did that so you can do it on the website without having like two boxes. You can just have it all in one text field and compile it. And the website is json.org, and I mean the way to try it is actually on the website, so you can experiment with it. And there's examples that load up on the try page. But moving down past the tokenizer, so we have the tokens. They're sort of like words. We have a sort of a higher conceptual level now, not just characters. We have tokens. So we move down to the actual defining what are valid combinations of those words. So a program, you can see the first one. So a program is a statement list and followed by an end of file. So a statement list, you jump down to that one. A statement list can be a statement followed by a period. And a statement list, the statement list rule is actually recursive. That's how you get sort of like a list. It recursively calls itself, so you can get a series of those statements. And the statement rule is either an identifier followed by is and an expression. And you'll see those mustache lines between the actual rule definitions. Those are the actions that are sort of building up the AST, because we want to transform the characters and the tokens into something, a data structure we can work with on the compiler end or the interpreter. So you'll see those action lines are just building up sort of an array that has what the token type is and some extra metadata about it. And we'll get into that a little bit later. But so a statement can be an identifier with the is token and an expression. So that's the assignment. And then show, which is our special built-in function to show the value with an expression. And then, of course, an expression can be an identifier, a number, or an expression plus another expression. So that's also kind of recursive, that you can define the expression to be defined within itself. So these will get expanded into either a number or an identifier. And that is the whole grammar right there, and talking about the actions a little bit more, the double dollar sign is actually sort of like a return value. So what are you going to return from that that action? And whenever whenever the parser matches, say, an identifier, it's going to run that action and return it. And then say this expression plus expression, these expressions are going to be whatever is returned by the identifier. So this action for the expression plus expression is going to be combining the result of one of these actions into there. So it's building up sort of the AST that way.
Do the $1 and $3, do those actually go back to capture groups in the regular expression?
Yeah, or well, not exactly the regular expressions, but whatever position the token is in the rule there, whatever position, the offset of the position of that token is what the $ number is going to reference to. So, yep. And then you'll notice that the top actually has a return statement, and that's returning the value of whatever the program is at that point. And so all of these, it's a bottom-up parsing algorithm. So all of the nodes sort of start at the bottom, and then it works its way all the way up to the program at the top, and then it returns that. But you could have a return statement like anywhere in the rules. It would exit out of the parser early. So and inside of these actions is all just JavaScript code. So those actions are just regular JavaScript code. You can put whatever you want in there. Right. Okay, so at that point, we have a grammar we can work with. And I'm going to show you a little bit of the code generation phase. So once you have your program parsed and you have a AST, so we just have like an array with subarrays, nested arrays inside of them. That's our AST representation. You could also create an object instead of just an array. You'd probably want to create an object, and CoffeeScript does that because, well, I'll show you how it looks here. Yeah. So we see our program again. And actually, this first line is, you'll notice that it's CommonJS require statement. So I'm using actually narwhal on the command line to run the parser. So that's just requiring the parser. Oh, actually, yeah. The way to generate the actual parser script. So you have your grammar defined in that grammar.json file. And if you want to actually create the script, the parser, because this is a parser generator, so it generates the parser, you'll use narwhal grammar.json, and that's what actually creates a JavaScript parser that you can include. It doesn't have any dependencies. You just include that JavaScript file and send it your input. It outputs the AST. So and I think I have it. Well, I already have a generated one already, so we'll just ignore that and get into the code generation file. So we've created our parser module and edit anyway. So we require our parser at the top, and again defined as our simple program. X is 5, Y is 6, Z is X plus Y. And then show Z. And then this is just some, our AST is what we return from our parse function. So the parser we generate has a parse function that you send in the input. So a string, a program, it returns the AST, which is in our case is arrays, nested arrays. And then we have a code generation function that we send the AST to. And at the end, we'll print the source out. But this code generation function is just, a big switch statement, and that's why This probably won't scale very well. If you want to do something like CoffeeScript, you create actual objects for each one of these nodes and have it have its own code generation function that you can just call on the object. So that, more object-oriented approach. But for this, was simple. I did this last night or something. So, it's basically just a big switch statement, and so you send it the AST, and the top array in the AST is going to be that program node. So it's the first part of the array is going to be program. It's going to call a helper function code generate on a list, which is here in this case just a reduce array reduce. So it starts out with a blank string and keeps appending on the next value in the. So yeah, it basically just code generates each item in the list, and then returns that. And that's going to be the last one that actually runs. So basically, it's recursive. All the children of the node get code generated, and then that gets included in that node's full text representation. So you can see a number is just going to return the value of the number, and an identity is just going to return the string that was the name, the identifier's name. Add expression code generates the first operand and then the second operand. And then the is statement, the assignment is just setting a name equal to. So this is generating JavaScript code, I should say. So even though it's an is statement, our assignment was a is, used is. When we're generating it, we're using the JavaScript syntax, so it's equal sign here. And then at the end, you can see the semicolon. And then the show statement is a print. So a show is we're just going to print out what that value is. If you're doing it in the browser, you do alert or console that log. And then if somehow some unknown node gets in there, you can throw. Right, and so that's the whole program. And if we run it, all right, so we ran the program, and you can see the JavaScript. I don't know if you guys can see it back there. The JavaScript program is what gets printed out. So those are the strings that we were building up in the code gen function. So it translated it from our syntax that we made up. We first defined in our grammar format, and then went through and actually generated this code here. Okay. And oops. Where's the mouse? All right, demo code generation. And instead of just compiling, doing this translation, you could also do meta circular evaluator, which is basically an interpreter that instead of just translating this AST into text code, it does a read eval print loop kind of thing. And if you want to know about all that stuff, yeah, it's a good book, especially if you're interested in programming languages. And I'm working on something called JSON. It basically looks kind of like Lisp, but instead of S expressions, it's JSON. So, and it pretty much looks just like the arrays we were building up, arrays with nodes, and that's what Lisp basically looks like. Lisp looks like an AST. So, it's sort of the same idea with JSON, but it's not really practical to write in because it's so verbose. You wouldn't really want to write in it for real, but it's great for experimenting with language ideas, because if you have your own interpreter, you can do whatever you want. If you want to create a closure and then have a way to inspect the context of the closure while you're inside executing code, you can do that. If you wanted to, you could basically any kind of introspection technique you can do, or anything you wanted at all. So interpreters are fun. So let's see. And that is the end of the talk. I just like that picture, so. All right. And there's a bunch of links that this gets posted somewhere. And I don't have that JSON on GitHub yet, but I'll probably put that up there. And And the demo that I did here. So, all right.